Okay, so thank you. Thanks for the invitation, Steve. It's a pleasure to be here. So I'm going to describe kind of the state of the art, at least at the NNSA labs in computational materials science, and where we're headed over the next decade or so as we look ahead to exascale and what the challenges are. And it's kind of hinted in this subtitle here that we really need to, as the architectures are becoming more heterogeneous and hierarchical, we really need to rethink algorithms and also the underlying middleware, the support for those algorithms to make them more heterogeneous and hierarchical. So as I mentioned, I'll start off describing the state of the art, kind of giving a few examples of what types of simulations are being done now on leadership class machines. And then just a couple slides kind of restating the obvious of why we can't just keep pushing this forward and evolving from petascale to exascale, what the major roadblocks are. And then get into a new project that's just started within the past month, a new center that we're kicking off to do this, what's been termed co-design, to march from petascale to exascale, working closely between the domain scientists, computer scientists, and hardware manufacturers to kind of rethink the algorithms and middleware and architectures to move towards these type of heterogeneous algorithms. So the computational materials science is a huge field. So it encompasses battery technology, includes chemical effects, corrosion, and other things. We're specifically interested in modeling the response of materials in extreme environments. And extreme environments in itself encompasses a huge range. So one thing the Office of Science within DOE is very good at is holding workshops, lots and lots of workshops. So the basic energy sciences part of Office of Science in particular has held a number of or term these basic research needs workshops. One was exclusively on materials under extreme environments, but several of the others, including in particular one on what's needed in designing advanced nuclear energy systems, pointed out the need for understanding the response of materials in radiation environments. On the more defense-oriented and weapons side, such as NNSA, the extreme environments that we're talking about are more mechanical environments, so collision, impact, high stresses and strain rates. So the mechanical environments are one that we're focused on, and then radiation environments for the nuclear energy field. So those are, even within this broad category of materials and extremes, the extremes I'm going to talk about are just these two, mechanical and radiation extremes. Some other workshops held by by Oscar, the Scientific Grand Challenges workshops, again, on the national security field and nuclear energy field, pointed out the need and the opportunity for modeling materials and extremes as we look forward to exascale, what types of new simulations and modeling can be done to, along with experimental programs such as the Energy Frontier Research Centers, some of which, this one in particular, Los Alamos, are looking experimentally at microscopic effects in materials as they're exposed to these extremes, to move forward and eventually understand and eventually design materials that are tolerant to these extreme environments. So that's the background. The way this is typically done, and so these examples are specifically Los Alamos and Livermore codes and work, is through a hierarchy, a series of length scales. So for each of the different scales shown here, from the electronic structure to the atomistic scale, through the mesoscale, and finally up to the engineering scale, the continuum scale, there are different computer codes and different models that have been developed over the years, and I'll give some examples in a minute. These have different, of course, different time and length scales that they can access, going from the microscopic all the way up to the actual system of interest. And they have various assumptions and kind of computational techniques under the hood. But the traditional way to do this is to start at the lowest length scale, using electronic structure calculations, determine what the equation of state of a material is. That is, as you compress it or heat it up, where it melts, at what pressure and temperature it melts, when it changes phase to different solid phases, what its mechanical response is, the stress-strain relationship. And then the other use of the electronic structure scale is to determine these interatomic force models, so potentials between atoms, that are then used in the next scale of modeling, molecular dynamics. So using these descriptions of the interatomic forces to model the response of materials under different loading conditions, so such as a shock wave going through a material. And so this gives insight into larger length scale phenomena, how defects and new phases nucleate and grow and move around. Those properties are then fed up to they're encapsulated in some model that's determined by a materials scientist working at this scale. That model is then fed into the next length scale, which is a mesoscale model that could be modeling discrete defects within the material or phases, phase evolution. That's used to determine the response at the mesoscale. It's encapsulated in some model that's then implemented in the continuum scale. So this is a very labor intensive. At each step along the way, the material scientist takes the simulations at the lower length scale, whatever experiments are available, whatever theories are known or postulated, to develop a model that's then fed up. So this kind of stepwise sequential multi-scale approach is what's typically done. And at each of these scales, so there's been a large amount of effort to develop custom codes at the labs for each of these scales, and several of them have demonstrated very, very high performance, and several Gordon Bell prizes and things like that. So down at the electronic structure scale, code QBox from Livermore, which solves the Schrodinger equation. Had to do things such as explore different domain decomposition schemes, and you wouldn't intuit from just looking at the algorithm that you get roughly a factor of 2 difference between these different decompositions. And this is due in part to the underlying problem in all quantum methods is that you're solving an equation that has the part of it is best represented in Fourier space, the kinetic energy term, and another term, the potential energy term, is best represented in real space, position space. So the frequent Fourier transforms back and forth and application of these operators results in this non-obvious decomposition scheme. Up at the mesoscale, another Livermore example from Livermore is this so-called parodies code, which is modeling the dynamics of dislocations within materials. So these are line defects within the material. So instead of modeling every atom in the system, it's modeling the evolution of these line defects over time. This is just showing as the material is strained, the evolution of these, and it becomes very inhomogeneous, and so load balancing is a major challenge. So for this, this has been applied to implement on systems such as Blue Gene series with some success. But in between these two, at the atomistic scale, this is a particularly simple algorithm. It's one that's really useful for exploring different approaches on new generations of machines. And in particular, the code that I've worked with at Los Alamos is this so-called SPASM code for scalable parallel short-range molecular dynamics. And the short range in here is the key. When we're looking at metals and organic systems, those interatomic interactions that I mentioned are fairly short range. There's a screening, so every atom only really sees its immediate neighborhood, and it only needs to know about the atoms nearby within some cutoff distance. So because of this fact, you can implement a straightforward domain decomposition scheme, subdivide your physical system among processors, and then further subdivide that system down to these subdomains of dimensions of the length of this cutoff distance. Then by doing this, the advantage is that for every atom, you don't need to store a list of all of its neighbors and maintain that list. You can just do a rapid search at every time step just by looking at all the other atoms within that subdomain and within the immediately adjacent subdomain. So this gives a straightforward order n implementation It's naturally parallel. It was first written back for the CM5 almost 20 years ago now, but it's evolved through a series of machines, was eventually did a major radical redesign for the new heterogeneous architecture of the Roadrunner system, and it's pushed forward to model systems as large as 1 trillion atoms in response to this. And so some examples here, a number of papers and different systems have been studied, ranging from mostly material damage as they're being strained, pulled apart, fractured in these different cases, up to the shock waves going through a material, and then also to systems including fluid dynamics, fluid instabilities in the material, and then a very different one, but kind of computationally similar, doing agent-based modeling instead of atom-based modeling to study disease transmission in networks of individuals rather than collections of people. So in this case, a so-called shock wave passing through a community of people instead of through a chunk of material to model flu transmission. So an example here, this is a somewhat old simulation, some 20 or 30 million atoms, just so that you can still see the atoms. In most of the simulations these days, visualization's a problem. You can't actually resolve on the display the individual atoms, but this is just one brief example of a shock wave going through a material, a sample of iron, and changing its crystal structure, with the colors here indicating the local crystal structure. Another example is, in this case, instead of looking at all the atoms, just looking at the defect atoms and seeing as a shock goes through and then an unloading wave comes through, how the material pulls apart and forms these voids and eventually fails by the nucleation of these defects, the dislocations I mentioned within the material, and then nucleating these voids that eventually link up and the material fails. So these are the types of single-scale simulations that are used to develop physical models for what's tensile stress and temperature and strain rate materials fail under these loading conditions. So these single-scale MD simulations can be pushed forward further and further, and there's a need for larger and larger scale. In particular, as we look at these polycrystalline samples, a typical material has is composed of different grains, different orientations. If you look at marble or other materials, you can see that the grains in metals, they're typically not visible to the eye, but these microscopic grains and this collection of grains determines the material response. It's long been known as the grain size in the material decreases, the material's strength goes up. But this can't continue forever. Eventually, as you get down to a grain size of 1 atom, you don't have a crystal structure, you have an amorphous material, and it has a much lower strength. So there's some turnover region here. This is actually a very popular topic in materials science, this nanoscale and Hall patch turnover effects. But if we want to understand the response of a polycrystal above this nanoscale, if we say we need, say, 100 grains to have a representative microstructure, a grain size well above this turnover of 50 nanometers or so, that puts us in the order of 1 billion atoms. If all we want to do is send a single sound or shock wave through the material, that puts us into timescales of nanoseconds. If we want anything more interesting to happen, we have to follow it for even longer, say microseconds. So we're looking at roughly 1 billion atoms for up to 1 billion time steps. If you look at what we can do on current petascale machines, so we're starting out down at the resolution of the system is at the 1 atom length scale. And to have a stable time-stepping algorithm, we need to resolve the atomic vibrations, of that atom, which requires a time step on the order of femtoseconds. So starting out down here, on a typical, say, Roadrunner or Jaguar or other systems, if we just fit all the atoms into memory that we can with, say, 100 bytes per atom, that puts us at roughly 1 trillion atoms. Of course, there's not much interesting that happens within a trillion atom sample in a few femtoseconds or even up to a picosecond. So we typically trade off system size, take advantage of this order n scaling to model smaller systems for longer times. So this gives us some linear scaling region. But eventually, as we do this, and the computational time step is in wall clock time shorter and shorter, we're eventually constrained by the overhead for each time step, just due to the communication and the synchronization, the barriers between processors. So there's a communication wall at some point, and this is just roughly what we could do on a typical system in 1 day of simulation. So of course this wall depends very strongly on the network, the interconnect, and it will vary from system to system, but ballpark, it's somewhere approaching a microsecond, somewhat less. As we go forward with the projections towards exascale, by definition, the floating point performance is going up 3 orders of magnitude. The projections from power and cost and constraints, and also some pushback from the application community, is that the memory capacity may go up 2 orders of magnitude. But the communication, and particularly the ratio of the communication to the flops, isn't going up much, if at all. So this limit is barely shifting at all. So as we go forward, this linear scaling region is getting farther. If you just do brute force molecular dynamics on larger and larger systems, you're really pushing yourself into a corner here. There's not much interesting that happens for very large systems at very, very short timescales. So we really need to address this timescale challenge and push out to longer length and timescales. Also on the architecture side, the way most of these applications have been pushed out on existing machines is just to run MPI on every core, an MPI rank on every core. So through the Blue Gene series, it was just easier to just do that and push on to 100,000 way parallelism rather than put in the effort to have a two-level or multi-level hierarchical algorithm. But given the GPU and the accelerator and the multi-core and many-core trends, there's really a need to recognize this, that as the architectures are becoming heterogeneous and hierarchical, the algorithms have to as well. Also the programming models and the underlying, the middleware, the software stack, there needs to be support for these hierarchical algorithms and architectures. We can't do bulk synchronous parallelism everywhere as we go forward to billion-way parallelism. And then the other traditional issues that are arising with power concerns, heat dissipation, fault tolerance as we go to these millions of systems, billions of cores, and resilience. Particularly silent errors. So what if something happens? How do we recognize silent errors, or how do we build algorithms that are resilient to silent errors? And then of course I/O is increasingly a challenge. We can't, just as we can't do this bulk synchronous parallelism forever, we can't do traditional checkpoint restart as often as we're doing now. We need to do more and more of the analysis and visualization in situ during the simulation. So given these trends, we've set up a center sponsored by the Office of Science, OSCAR, to co-design the algorithms, the middleware, and then working with vendors, the architectures to do these types of, to move from single-scale material science to scale-bridging applications using an approach such as this, whereas, say, a shock wave is going through a material, we have very good continuum models ahead of the shock and behind the shock for the material. It's only during that transient where we don't have good constitutive models for materials that are changing phase, what the strength is at each point in time. It's very difficult to develop a model for that, but you might imagine spawning off finer scale simulations to just directly compute the properties, the response of the volume element at that state. If we have all these processors available and for other reasons, it's much more advantageous to spawn off tasks to compute the properties of this. So this is our goal. These are the partners involved. I should mention there are 3 of these centers. They've just, well, the other 2 are looking at combustion, led by Sandia, and nuclear reactors, led by Argonne. And they've just launched within the past month. So we had our kickoff meeting a couple weeks ago, and the other 2 centers are having theirs this month. So these are brand new 5-year centers that are just starting. As I mentioned, co-design is the goal here to have these communities working together. So instead of having vendors targeting performance metrics at some widely used benchmark that may not be representative of the actual workload, probably isn't. Instead of optimizing systems for static benchmarks like that, and instead of having application developers insist on carrying their legacy code forward without any changes, or writing their code with a vague or incorrect vision of what the machine looks like, actually getting these 2 communities working more closely together to sit down and develop the applications, the middleware, and to what extent they can push the hardware in directions that can take advantage of this. So this is nothing new. Back in the old days when custom-built systems were, before the commodity systems were around, the initial systems at Los Alamos and elsewhere, it was a close collaboration between the application scientists and the architects developing machines such as the Maniac here. It's gone forward as more complicated machines like Roadrunner came along. So again, it was the first petaflop supercomputer, is the first heterogeneous and accelerated one using the cell processors. And it really, developing applications, it wasn't porting applications, it was really rewriting, developing new applications for Roadrunner, involved a close collaboration between the computer scientists and the domain scientists. So there were a number of projects these open science projects, and the ones that succeeded and had a close coupling between a domain scientist and a computer scientist. And also interaction between the computer scientists who could benefit from common kind of tricks and algorithms used in one application for a very different one. So the goals of this co-design project, again, are to establish this interrelationship. It's not just the hardware and application. Middleware is also a key challenge, as I'll describe in a minute. And instead of evolving things forward, thinking of how we can take advantage of these changes that we're facing, the concurrency, heterogeneity, and flop byte ratios that are going to be very different in the 2020 exascale time frame. So again, doing this, we have this so-called adaptive physics refinement approach, which is a task-based method, which I'll describe in a second since I'm running short. Kind of the key objectives for how co-design is actually done on the floor. The main thing is the idea of proxy apps or mini apps, flexible, kind of manageable code examples that exhibit the workload, the communication, not just the mathematical kernel, but also the flow between processors, between tasks. And also can be used to explore different algorithm choices. So instead of starting with the full-scale legacy application, work with these simplified proxy apps that can be passed between the application community, the applied math, and to the vendors for their modeling, and explore the different architecture and algorithm choices, and assess the performance of these for the applications for the performance, the power, fault tolerance, and other things. This requires the use of heavy use of models and simulators, things like the SST simulator built by Sandia. Also some emulation to kind of stress test these algorithms and introduce faults and perturbations, latency, exploring the tails of distributions that would crop up as we go to billion core parallelism to test these things and assess the algorithms and architectures for these so-called P3R, the price, performance, power, and resilience. Let me skip over these, just point out, I showed the institutions. We have a number of kind of 3 scientific pillars in these different task areas that are involved. Los Alamos, we're leading at Los Alamos. Livermore is a strong partner, and then Oak Ridge, Stanford, Caltech, and Sandia are also involved. Let me skip this. I should mention that there has been work done on this task-based approach, so-called adaptive sampling technique, demonstrated at Livermore, where again a finite element is running at the top scale. It queries a database for a fine scale response at the volume element. If that response isn't known, it spawns off a task to compute that response using a smaller, finer scale model. This kind of example really pointed out the need for an underlying middleware support of task-based approaches like this. So this was kludged on to existing MPI and Slurm systems libraries, but there's really a need looking forward for having support for task migration, reissuing tasks if there's been a failure, and things like that. So it's not just the applications and the hardware level, as pointed out earlier. The software, the middleware layer, is really becoming an increasing challenge as we go forward. And who actually owns that? So there's, at the national labs side, the kind of the sexy piece is the top 500 list and where you are in flops. So typically most of the money's going towards buying more and more flops and less towards the things that we actually need for useful systems, the file systems, and the middleware. So this is a key piece as we look towards this co-design. So finally, one other example of this, so this adaptive sampling that I mentioned is more for the mechanical extreme condition. One last thing on the radiation extreme, there's a similar methods that are used, so-called on-the-fly kinetic Monte Carlo, where a typical way of modeling the evolution of a material in response to radiation damage is to have a catalog of possible mechanisms and do rate theory or kinetic Monte Carlo to evolve those defects in the material. But if you don't know what the possible mechanisms are, you can spawn off finer scale tasks to update this rate catalog using finer scale simulations. So that's the example on the radiation side. And since I'm out of time, I'll just close there. So, thank you.